Okay, just a quick video to go over a couple of questions I received from a student today. First question was, how come we can't expand question 17 the same way we did question 3D? And this is in the dot product section. So this was question 3D, just to sort of clarify, and we see that dot product, or we know that dot product is distributive. And so we multiply the first term by each of the three other terms, and so on, exactly as we would have with any kind of a polynomial expression. Get this out of the way. So this is question 17, and I'll show the solution that the textbook uses, and it's probably the one that I would use normally as well, but we'll go through it by expanding first. And so given this and this are vectors in IJ notation, I always convert to regular Cartesian notation. There's no real reason to have the i's and the j's when this says exactly the same thing. So that would sort of be my first step all the time, no matter what kind of solution I'm going to go through. Now, if we want to expand the dot product here, we can do that. 4a times 3a is 12a. Sorry, 12a dotted. 4a times 2b is 8a dot b, and so on. We get minus 3a dot b and minus 2b dot b over here. I did the dot products off to the side. So a is negative 2 times negative 2, again multiplying the x values, or the first values, and adding the multiplication of the second values. So it's 29. You can check this on your own afterwards, but 29, negative 37, and 50. And then basically just plug those back into the formula. So I've got 12 times, or to the expanded form here, I've got 12 times the value 29, 5 times, and so on, and we get the answer 63. After having done that, I copied over the solution from the textbook, which again was the one that I would probably tend to go with. And I'm guessing once I do that, or I was guessing once I did that, that probably just the student looked really quickly, saw 53 and said, oh, I got the wrong answer. And of course, what happened was 36 plus 27 is in fact 3, carry the 1, 63. And so the textbook had the wrong answer. So it's possible that I did all this for naught, but that would be my explanation. Well, sorry, my explanation as to why you cannot. You certainly can. Probably this is a slightly neater solution to put the numbers in, but certainly there's no problem doing the algebra as well. And then the other two questions were, I think, fairly straightforward, but I wanted to make sure that I answered them here as well. What exactly does square brackets mean? Unless I'm misinterpreting the question, you're basically asking, what does this mean versus something like this? This is a point on the Cartesian plane as it always was. Okay, so we've got our little coordinate axis over here, and the point 36. Let's change some colors. So the red value here is 1, 2, 3, 1, 2, 3, 4, 5, 6. It's this. And the blue value is this. Okay, so that's the difference. The square brackets indicate that we have a vector. The round brackets indicated, as they always did, a single point somewhere on the Cartesian plane. And then last one, why does I plus j equal 1, or wow, why does I plus j equal square bracketed 1, 1, also equal 1, 0, and 0, 1? And so basically what we want to recognize is what each of these things represents. This is my I. I is a unit vector in the horizontal direction to the right. J is a unit vector in the horizontal, or in the vertical direction up. So this is J. Oops, close enough. And when we see the plus sign, so going back to what we sort of started with when we very first did some vector stuff, to add two vectors, we put them tip to tail, so the tip of I to the tail of j, and the resulting vector ends up being the vector that runs from the tail of the original to the tip of the first one, or sorry, tip of the second one. And then basically what we're looking to determine is what does this, what is this vector? Well, based on what we've said before, it is, we define it in Cartesian plane as the amount of it going x, the amount of it going y, or the amount of it going to the right, the amount of it going up. And so just if we think about what that represents, we have a 1 going to the right, we have 1 going up. Square brackets indicate that that's a vector. And so this vector would be defined by this coordinate as well. So I would say, are you simply allowed to add the brackets together? Technically, yes. Whatever x value I have for one, if I'm dealing with two vectors kind of in a less obvious direction, something like this, where my one vector is maybe, say, 5, 3. Whoa. And my other vector is, say, -2, 4. If we do put those together and add them, the resulting vector ends up being 5 this way, and then back 2 more this way, so a total of 3 to the right, and 3 up, and 4 more up, and so 7 up. So when we know the coordinate axis, when we know the Cartesian vector, we can just add the two x values to get the x value of the resultant, add the two y values to get the resultant for the y values.